Today, we're going to talk about a story that comes from the very heart of mathematics. It's a story about certainty, about doubt, and about this really incredible intellectual tradition. We're diving into a Japanese legacy that was built on one of the most fundamental questions you can ask. How do we know that math actually works?
I mean, just think about it for a second. What if the code that runs our entire world had a fundamental flaw? What if the logic we use to build everything, from bridges to rockets to all our secure data, was built on some kind of hidden contradiction? You know, for mathematicians and logicians, this isn't just some scary late-night thought. It's the central challenge of their entire field. It's this decades-long quest to prove that the rule book of mathematics is solid, that it's consistent, and that it won't ever lead us to some crazy, impossible conclusion like 1 equals 2.
Okay, so let's start right there, with this fundamental quest for consistency. What does it actually mean to prove that math itself is reliable?
Well, think of it like this. A consistency proof is kind of like a master inspector who goes through the entire rulebook of a system, say arithmetic, and meticulously checks every single line. They're making absolutely sure there are no contradictory rules, no hidden loopholes that could let you prove something is both true and false at the same time. Because if that happened, the whole logical structure would just collapse.
So right in the middle of the 20th century, this global quest gets a powerful new champion over in Japan, a mathematician who would pretty much ignite a legacy. His name was Gi Takayuti. And listen, Takayuti didn't just contribute to the field, he basically established it in Japan. And he did it fast. I mean, in just 6 years, between 1949 and 1955, he published this flurry of foundational papers, one after another, all of them tackling what he called the fundamental conjecture.
So what was his secret weapon? It was a really powerful technique called cut elimination. Imagine a mathematical proof is like a road trip from your starting assumptions to a final conclusion. Cut elimination is like a GPS that gets rid of all the scenic routes, all the unnecessary detours, and finds the most direct path. By showing you can always find this direct path, you prove the system is clean, it's direct, and it's free of any hidden logical traps.
And this is the really key part. Takayuti's work wasn't the end of the line. It was the beginning of a story, an intellectual inheritance that would be passed down and built on for generations. He basically lit a torch that's still being carried by Japanese logicians today.
And that inspiration, it took hold almost immediately. Takayuti's ideas sparked this huge wave of work among his colleagues, and suddenly you had this vibrant community all wrestling with the same kinds of big questions.
And this expansion just blew up across all these different fields of logic. For instance, you had Satoro Kurota, who took these methods into intuitionistic logic, which is a system where a proof has to be really constructive. Then Shoji Miyahara focused on predicate calculus, the logic of properties and relations. And then a huge breakthrough came from Motoo Takahashi, who proved cut elimination for type theory, which is a system that's absolutely crucial for modern computer science.
So you see, this wasn't just students copying their teacher. No way. This was a true intellectual explosion. Each of these logicians took Takayuti's core ideas and ran with them. Applying them to new and different corners of logic, they built this wide, robust foundation for all the incredible work that was going to follow.
So the next generation of researchers took these methods and just applied them to entirely new domains, pushing the boundaries of what anyone thought could be proven. First up, they went right for the core. Researchers like Toshiyasu Arai and Kokio Shirai took on this massive task of providing new consistency proofs for arithmetic itself. Yeah, the math of numbers we all learn as kids. They fine-tuned the original methods, making them even stronger and more elegant. But they didn't stop there, of course. They moved beyond classical logic into totally new territory, like modal logics. These are the systems that deal with concepts like possibility and necessity. Researchers like Onishi, Matsumoto, and Ono started showing that Takayuti's methods were super versatile, enough to check the rulebooks for completely different ways of reasoning. The reach of this tradition was just incredible. I mean, get this. The methods were even applied to one of the most counterintuitive fields you can possibly imagine, quantum logic. H. Nishimura and M. Takano actually developed systems to analyze the bizarre rules that govern the quantum world, proving just how powerful these foundational ideas really were.
And this tradition isn't some dusty old thing in a museum. It's alive and it's evolving. Today, you've got researchers like Ryo Takamura developing systems that combine the old-school formulas with diagrams, and others like Takeo Inoue are using different but related methods to keep investigating the consistency of arithmetic. The quest just keeps going.
So, when we step back and look at this whole story, from the middle of the 20th century all the way to today, what's the real, enduring legacy of this incredible body of work?
What we see is this remarkable unbroken chain of inquiry that stretches all the way from Gi Takayuti to the present day. It's a tradition that's really defined by a deep focus on the power of cut elimination, but its impact has spread far and wide, from basic arithmetic all the way to the frontiers of quantum physics. At the end of the day, it's a story of how one person's powerful idea can be inherited, expanded on, and innovated upon for generations.
And that kind of leaves us with a final thought, doesn't it? These mathematicians, they spent their lives making sure the logical foundations of their world were secure. So, in our age, an age completely run by complex algorithms and artificial intelligence, what's the next fundamental rulebook we need to check? What's the next consistency proof we need to build a future we can actually rely on?